So in the previous videos about the introduction to communication systems, we talked about what analog communication is, what digital communication is, and the main reasons why we move or why there's a shift from analog to digital communication. So we saw that the noise, it's much easier to remove the noise in case of digital signals, and it's much easier for the receiver to identify between two voltage levels or two values, zeros and one, instead of the whole range of values that exist in the analog signal. So we're living in the digital world today, and that's the reason why in this course we're just going to concentrate on digital communication. And some courses will, you can learn analog communication for historical reasons if you feel like, if you're curious about it. But we're going to begin with digital communication. So the first thing is, in case of a digital communication, the source of the information is giving out is a digital signal, right? So the first thing is that the all the signals that occur in nature that we transmit through the channel are usually analog signals. So we should first know how to convert an analog signal into a digital signal for the transmission of the digital signal, and then we receive the digital signal, but we convert it back into an analog signal for the destination, right? So let's take an example of a speed signal. This is the most common signal that you might relate to when you're studying communication systems, because communication, it may be in the form of it may be any data, but speech is the major form of communication. So let's first look at how a speech signal looks. So this is how a speech signal looks. Okay, I'm gonna just record a new one for you. So as I'm talking right now, you can see this signal as an analog signal. Okay, it is taking a range of values. So let's suppose this is the analog signal that we need to convert to a digital signal, and I'm sorry, this is the origin. So what you do here is, the first step is that you sample the signal. Okay, you sample the signal. These are you just take random values at equal intervals, but this depends upon the sampling filter that you've used, sampling frequency of the filter. So this is the first step. The second step is that you quantize the signal. Okay, before we do that, we just mark out the sampled values, okay, on the signal, of course. Right. The second step is to quantize the signal. You take quantization levels, which are voltage levels at different voltages. Let's say this is 1, this is 0.5, let's say this is 1, this is 1.5, let's say this is negative 0.5. Okay. So just draw these levels, okay, and that's your quantized and sampled signal. The next thing that you need to do is you need to approximate the sampled values to the nearest quantization level. Okay, just write this down. Approximate the sampled value to the nearest quantization level, right? So let's see how we do this. We have, this is the first sample value, and the nearest quantization level is 1.5, right? This is the second sampled value, and the thing in the green, and the nearest quantization level is again 1.5. For the third one, it's 1, and so on and so forth. 0 is also a quantization level, right? And again a 0, I guess. Okay, let's just take 0.5. Let's just assume this is closer to 0.5, and this is 0.5. So now let's just write down these values. We have 1.5, 1.5, 1, 0.5, 0, negative 0.5, and a 0.5 again. So definitely these values, these set of values that you wrote down after the sampling and quantization and approximation, the three processes, is always going to be composed of the quantized levels, right? So you've translated the signal into a set of quantized levels. So this may now look like a discrete signal if you try to plot the signal, right? These are just random values, random voltage values. Now what we need to do is convert this into a digital signal. So what we do is we write a binary code and we translate each quantization level into a particular binary code. So we'll start with, and now since there are how many? 1, 2, 3, 4, 5. There are 5 levels. So we need at least a binary word consisting of 3 binary digits to show 5 levels, right? Because 3 digits, binary words consisting of 3 digits can show 8 levels, right? It's 2 to the power 3. Okay. And if you had just 4 levels, if you had just 0, 1.0.5, 1 and 1.5, then you could just use 2 binary digits. Because 2 binary digits can be used to show 4 levels. Okay, 0, 0, 0, 1, 1, 0, and 1, 1. And in this case, we're going to use 3 digits. So it's going to be, okay, and we just need 5 of them. Okay, so this corresponds to 0, negative 0.5, this corresponds to 0, and so on. And now we need to translate this whole thing based upon the binary digits that it corresponds to. So we get, for 1.5 it's 100. For 1.5 again it's 100. For 1 it's 011. So we can just write this down. It's 1.5, 1.5, 1, 0, negative 0.5, okay, and 0.5. And again 1.5, 1, 0.5, 0, negative 0.5. This corresponds to 0, 0, 0. Okay, so what we have now is we have 100, 100, 011. For 0 it's 001. For negative 0.5 it's 000, and for 0.5 it's 010. Now this is a set of zeros and ones, so this is a binary representation. But now the thing is that the signal was a voltage signal, right? And now we need to translate this binary representation into a voltage representation. So in this case, let's just assume that 0 is represented by a voltage level 0 and 1 is represented by a voltage level plus V. Okay, this is something that you're gonna see later in line coding techniques, but right now just consider that a 0 will correspond to a voltage level equal to 0, a voltage equal to 0 volts, right? And 1 would translate to a voltage level plus V, a voltage equal to plus V volts. So the whole thing can now be written as something like, okay, we're gonna first leave a little space, and I'm gonna tell you why. So we have 1, 0, 0. Okay, we're going from here, 1, 0, 0, and then we leave a little space, and then we have 1, 0, 0 again. Now we again leave a little space, and then we have 0, 1, 1, right? Leave a little space, and then we have 0, 0, 1, and this goes on. Okay, now the thing is that this is, now when you have this whole signal at the receiver's end, you need to take out the same information again. Remember, it's always going to be a mirror image when you go to the receiver. So we first need to translate this voltage representation. Remember, this is plus V and this is 0. Okay, we need to translate this into this. So this is why we leave the extra space, so that it's easier to identify individual binary words. Like this is a binary word, right? This is again a binary word, this is a binary word, and this is a binary word, and these 0, 1, 1, these are individual binary symbols. So a binary word in this case consists of 3 symbols because we need to show 5 different voltage levels. Up to 8 levels, we can just use 3 symbols. Now, this is where the problem comes. Let's say when the signal transmits through the channel, you have you definitely have a lot of noise sources, you have noise imposed on the signal. So how do you remove the noise?